Alright, welcome to another AQA A-level chemistry video. This is the part 6 and the final video on this series of videos for exam style questions on acid bases, or exam style questions on acids, bases, and buffers. Alright, so I'm going to go through one last question, really easy question. I actually want you guys to do this yourself, so pause the video now and try and do it yourself. So as soon as you've paused the video and you try to do it yourself, after this, I'll actually go through one small little thing to do with conjugate bases, because I said I was going to do it. Or said, at least I said I wasn't going to do it. And then I think I just changed my mind, just because it's only a couple of seconds to actually, or a couple of minutes to do. So, yeah, I'll go through that. So anyway, I'm going to go answer the question now. So the question says 31 centimeters cubed of sulfuric acid is needed in a titration to neutralize 46.3 centimeters cubed of 0.15 moles per dm cubed potassium hydroxide. Use the information provided to calculate the concentration of sulfuric acid used, and in your answer include the balanced equation. Okay, so I'd probably do the balanced equation part first, because that's just like pretty easy. This is just a very basic neutralization. Really sorry about that. That's from all the way up there. These are all the videos I've been doing. So yeah, potassium hydroxide. What's this? We said it first. Sulfuric acid, isn't it? I'll start with sulfuric acid, but even though it doesn't really make a difference. Sulfuric acid plus well, I already know it's 2. It says balanced equation. I already know it's 2 KOH, because you have 2. It's diprotic, so we're gonna have 2 hydroxide ions there, and then you're gonna form K2SO4 as a salt, and then plus 2H2O. Check that's balanced. 4. Why is that a minus? That's not a minus. Sorry. 2. So you always got to check back your answer. 4 hydrogens, yes. 2 potassiums, yes. 1 sulfur. Yeah, good. And in case you the way I do it, just to be certain, it doesn't take you a lot of time to do. I just think of all the elements that we have here: H, S, O, K. And by the way, if you just want to skip to the answer, just go skip to the answer. But this is like what I think about whenever I answer these types of questions, because it only takes you a couple of seconds to do this. But in case you can you're not sure about balancing equations, which you should be able to balance equations by this point in time. But in case you're not certain about your answer being fully balanced, you can just do a little table here on either side and just go like H, S, O, K, H 4, S 1, O is 6, K is 2, and in this side we have two potassiums here. Oxygen is 6, sulfur is 1, the hydrogen is 4. 4, 1, 6, 2. Again, this is only if you don't know how to balance equations, but at this point in time, you should be able to balance equations. But just in case you that's a little thing you could do there, just to make sure you got your answer correct. But anyway, let's actually answer the question now. So, concentration, moles, volume. I just do this little table because the only thing that involves here is our sulfuric acid and our potassium hydroxide. So that's only 2 that we have to think about here. And I want us to calculate the concentration of sulfuric acid needed to neutralize this potassium hydroxide. So concentration here is of that's what we're trying to find out. Volume is 0.031. Volume here is 0.0463, so 0.0463. Concentration of this is, or the 0.15, so concentration of potassium hydroxide is 0.15. It's a 1 to 2 molar ratio here. Moles of I can clearly work out the moles of potassium hydroxide. So moles of potassium hydroxide is equal to, or moles first of all, is equal to concentration times by volume, and that's 0.0463 multiplied by, well, that's actually the volume. So let's do it in order, the order that I have it here, so I don't confuse you. The concentration is 0.15 multiplied by 0.0463 put that into a calculator. 0.15 multiplied by 0.463. 6.95, if around that. 6.95 times 10 to the power of minus 2 moles. It's a 1 to 2. So in this case, it'd be 2 to 1 mole ratio. So the moles of H2SO4 would be equal to 6.95. I just write out a statement saying it's going to be half of that, but you don't really get a mark for saying that. You get a mark for actually doing that. So divide that by 2. That's 3.47. So 3.47 times 10 to the power minus 2. Alright, so then concentration is equal to moles over volume. Therefore, concentration, this should take you 2, I think this is like a 3-mark question maybe. I mean, if you're including the last one now, I'll do the marks at the end, but it should take you 3 minutes to go and do this type of question. Concentration is equal to moles over volume. So 3.47 times 10 to the power minus 2 over your volume, which was 0.031 decimeters cubed. If you didn't get the volume, that's in decimeters cubed. So this is 31 divided by 1,000, because remember this is in this was in centimeters cubed. We need it in decimeters cubed. So 31 divided by 1,000, or times 10 to the power minus 3. That's how we got 0.031, in case you're wondering where I went from there. Again, I've always said this in my previous videos. And you should get an answer of 1.12 moles per dm cubed of H2SO4. And that's it. Okay, so marking for this, they said they want you to include the balanced equation. So a mark for a balanced equation, only 1 mark. They definitely just be 1 mark for a balanced equation. A mark for each of the moles, and then 1 mark. So probably this is a 4-mark question. So 4 minutes to do. All right, so this is the one last. So I've done all the questions now, so there's no more questions left. This is just me going a little bit through conjugate bases, because I think one person asked, well, what are conjugate bases? So I'll explain. So when it comes down to acids and bases, we describe them in terms of pairs, conjugate pairs. So we have conjugate, a pair of conjugate acids and conjugate bases. Now, here I've got an example of an acid-base reaction. Well, it's really an acid dissociation reaction. The first one here. Let's look at the first one here, right? It's an acid dissociation, or we're just dissolving the acid in our solution of water, in our solvent of water, to form this solution here, right? So HCl is aqueous because it's dissolved in water, and in water it will go to form H3 plus Cl minus. So this is a reaction here where it's really a dissociation, but this would let me change color pen here. Technically, this H3O plus will just dissociate again. This hydronium ion. This is technically how it is in a reaction in solution. It'd be a hydronium ion, but that hydronium ion can dissociate into H plus and H2O. Right, but just that's not what we're looking at here. That's not what we're looking at here. We're looking at, remember what our understanding of what a Bronsted-Lowry acid and base is. I just want to think about Bronsted-Lowry acids and bases first, right? A Bronsted-Lowry acid is an acid that donates a proton to another substance. It's a proton donator. That's a 1 mark. That's a 1 mark question, by the way. They may ask what's a Bronsted-Lowry acid. It's just saying it's just a proton donor. 1 mark. That's it, right? So if we're looking here, which one of these two between water and HCl is acting as the acid? And now I know this is very obvious which one is the acid, but why is that the acid, right? I want you to think about it. So obviously HCl here is obviously the acid, but why is it the acid? Because it's the one that donates the proton here. You can see here, right? It donates the proton. As it comes down to it here, That's the base, right? That's the base. This is the acid. So for every acid on your reactant side, you form a conjugate base in your product side. And if I was to highlight it, acid conjugate base, right? Because it's donating the proton to the water here. It's donating a proton to this water molecule here. And so that's where we form now this conjugate pair. Oh, actually, I wanna. So losing this proton here to the water, right? But in total, that's one conjugate pair. And here, what we have in this essentially in a reaction, you'd have two, in a straightforward reaction like this, you'd have two conjugate pairs, right? So we've already found out what one of the pairs is. Now we already know that H2O in this case is acting as the base because it's accepting a proton, but we can actually just see it here. Look, the H2O is gaining a proton here, and this is acting as so this is acting as the base. So I'll get my say so base because it's gaining a proton. This will, if this is going in the reverse direction, right? So let's say this is going in the flipped direction and equilibrium shifted to the left. H3O plus would be acting as I said before, hydronium ions are an acid, right? They dissociate. I just showed you before how hydronium ions would dissociate into H plus and H2O. So this here is our conjugate acid, right? Conjugate acid here. So that's all that they are. That's all they represents here, right? I've got another example here, where let's do a base reaction, right? I do believe that this is the correct way of doing it. Apologies if it's not but however, right? The idea is that I'm showing you what's going on here. If this isn't the correct way of showing it, but my explanation will stay the same. So here we have a acid base, was technically still an acid base reaction, but it's a base being dissolved in water, right? I should have done my my state symbols here of aqueous, liquid, aqueous, and aqueous. Yeah. So here's the base. So we can, if I was to ask you again, which one's acting as the base and which one's acting as the acid in the reactant side between potassium hydroxide and the water, again, you can very easily tell here that potassium hydroxide is acting as the base, right? So, but again, why is it acting as the base? Because if we're going back to Bronsted-Lowry acids and bases, a Bronsted-Lowry base is a proton acceptor. That's a 1 mark answer. Or proton acceptor accepts a proton. Where's accepting a proton from? It's accepting a proton from the water molecule here. And you can see that here. So here we have our Bronsted-Lowry, our Bronsted-Lowry base conjugate acid. Why this is a conjugate acid? Because this will just go back to form. It doesn't like to be KOH2 plus. It would much prefer to be. I'm gonna put I believe that the H plus should be. Well, not to make sure everything is. It'd be on the oxygen actually, but I'll leave it on the outside here. It'd be on the oxygen because the oxygen would be the one that's more positively charged in that case there. Because I can leave that there because it's gonna lose a H plus anyway. So the way I understand this, K, right? It's gonna want to do this, and in this gets ejected off as a H plus, and you have KOH here, right? That's what's happening here. So this KOH2 is acting as is our conjugate acid, because if we were to flip this reaction round, right, the H plus would then react with a, because this is a the H plus will react with another OH minus to form water, right? But the point being, this is clearly, you can clearly see here our conjugate acid, so conjugate base there with the potassium hydroxide and forming, sorry, our acid and our conjugate base. I just messed that round, sorry. I've messed that round, sorry. Our base and our conjugate acid. There you go. Sorry. Mixed them around. And in this, and that's one pair. That's just one pair between these here, right? That's one pair here. So our base and our conjugate acid here. So then, remember I always said that water is a funny one because it always acts as a, it can be classified as both an acid or a base. And I've just shown you in this example here. Remember the top example I showed you, it was acting as a base. Here, water is acting as an acid because it's able to donate a proton to the potassium to form an OH minus here. So this is our conjugate. This is our acid, and here we have our, on the hydroxide scene here, this is our, clearly our conjugate base. The water's acting as the acid, the hydroxide ion is our conjugate base from that reaction. Right. Now, why is this important? Because, I mean, why would we see this as being important, right? Because the reason why this is important, because it allows us to understand, because sometimes it's not obvious. Where this is a very easy example here of seeing which one is the acid and which one is the base. It's very clear to see here which one is acting as the acid and which one's in either example. It's very obvious that we already know that HCl is already the acid and potassium hydroxide is already the base in either of the examples here. But sometimes it's not so clear here, right? So when we're going back to what reaction would this been? It would have been with nitration reactions, right? When forming the nitronium ion, right? We act concentrated sulfuric acid with concentrated nitric acid here. This is an acid-base reaction here, but it's not easy to see because they're both acids. They're both strong acids, but one of these two is acting as the base, and one of these two in the reactant side is acting as the base. Another one is acting as the acid. Why? Because so I've got another example down below. Don't worry about this example here. This here, you can clearly see that. Actually, I want you guys to see which one it is. I want you to pause the video now and try and guess between which one of these two is the acid and which one is the base. Alright, so I'm assuming you pause the video now and try to answer the question, right? I can tell, kid, that let's look at, I already know the answer, but let's just see, look what we have here. The H2SO4 is going from H2SO4 to HSO4 minus, right? Whereas HNO3 is going from HNO3, right, to H2NO3 plus. So here, the H2SO4, right, the H2SO4 is losing a proton and forming HSO4 minus. Therefore, the H2SO4 is the one in this case acting as our acid, and a HSO4 minus would be acting as our conjugate base, right? And I say conjugate because it's acting as a conjugate base because in the reverse reaction, if the equilibrium was shifted to the right, to the left, going in the reverse direction, this here would be gaining a proton, right, to reform H2SO4. But then if that's one conjugate pair, right? This is one conjugate pair. What about the other conjugate pair? Well, we know now that, look, the HNO3 is gaining a proton, which means that this must be a base, and this must be the conjugate acid, because if the reverse reaction, we lose a proton, we donate a proton to to H2SO to H2SO4 to form HNO3 if you're doing the reverse reaction. But it's interesting, right? It's very clear to me now that you understand what conjugate basis, conjugate acid is here, because they can ask you a couple 1 mark questions where they put a box underneath and a couple of equations, and they ask you which one's the acid, which one's the base, and put a B if it's a base, put an A as an acid. I've seen exams have questions like that. But it's just about you understanding that, because you wouldn't usually see it here, like strong nitric acid here is usually a very, very strong base. So it's a very, very strong acid. It's usually a very, very strong acid here, nitric acid. Whenever you think about nitric acid, it's in the name, right? It's an acid, but not only an acid, it's a strong acid. But in this particular example here, it's acting as a base because it's accepting a proton. And that's why that's our understanding of conjugate bases and conjugate acids, if you didn't get them before. Now, I did that by accident, really. Alright, so now we've got this last example here of an acid reaction with a base to an extent, right? Or you can say a base, but it is a reaction. It is an acid here reacting with base, but it's not in the way that you think it is, because usually our understanding of acids and bases is related to Bronsted-Lowry acids and Bronsted-Lowry bases. But I'm going to leave a link in the description to that video, because in that video I also talked about Lewis acids and Lewis bases. There's not only one type of understanding of the base. There's Lewis acids and Lewis bases, and it's used for this exact example here. This is an acid. Well, this is an acid reaction. This has an acid, a very obvious acid here reacting it. But you're not thinking about it like an acid. This is an acid-base reaction. Now, remember what a Lewis acid is. Remember, a Lewis or Bronsted-Lowry acid is a proton donator, but a Lewis acid is a lone pair acceptor of lone pairs, and that's also 1 mark answer. And the a base is going to be vice versa to that, where it's going to be a Lewis base is a lone pair donator. So here I'm going to be looking at what's gaining in a lone pair and what's losing a lone pair here. Now in this case, AlCl3 is the one that's gaining a lone pair, because here it's going from no overall charge here to a -1 overall charge on our peroxide as it forms AlCl4, whereas and Cl2 is going from no overall charge as it is in the reactant side to a +1 overall charge in our peroxide. So here you can see the Cl2, I really should say this isn't even balanced, sorry. It should be no, it is balanced. No, it is balanced. My bad. It is balanced because the Cl goes from here, right? But as you can clearly see here, Cl2 is what Cl2 is. This is almost a disproportionation reaction here. Let me just check 0 + 1 here. I don't know the oxidation state of aluminium, but I'm not going to call it disproportionation reaction because I can't tell what chlorine is, the oxidation state of chlorine here is. However, what I can say is that this is definitely an acid reaction, because the AlCl3 is gaining a lone pair of electrons, and the Cl2 here is losing a lone pair of electrons as it forms Cl+ here. So this is our acid, and this is our conjugate base, right? Here we have our technically our base, and this is our conjugate acid, because this would then, if it were to cause equilibrium, if equilibrium shifted to the left, right, this Cl+ here would gain a lone pair of electrons to reform Cl2, and this AlCl4 minus would donate a lone pair of electrons to form AlCl3, will donate a lone pair of electrons to Cl4 as well as a Cl- here to reform Cl2. And when it does this, it's acting as a base because it's donating a lone pair of electrons. And so that's all of it. That's the end of this video. That's the end of this little part series here. Hopefully this video helped, and that is it.